So what's an ideal fluid? Many features of fluid motion can be understood by considering the behavior of an ideal fluid, which satisfies the following conditions. 1. The fluid is non-viscous. There's no internal friction force between adjacent layers. 2. The fluid is incompressible. Its density is constant. 3. The fluid motion is steady. The velocity, density, and pressure at each point in the fluid do not change with time, and the fluid moves without turbulence. This implies that each element of the fluid has zero angular velocity about its center, so there can't be any eddy currents present in the moving fluid. So just like we've done before to try to make the problem solving a lot easier, we state conditions that make the fluid flow, in this case, ideal. As a fluid moves through a pipe of non-uniform size, the particles in the fluid move along the streamlines in a steady state flow. So we can see here as we lay out this diagram, and we've got some cross-sectional area 1, cross-sectional area 2 at the exit. We've got some velocity 1 at the entrance, velocity 2 at the exit. We've got some distance that the fluid moves and some distance that the fluid moves. Okay, so as the fluid moves through the pipe of non-uniform size, the particles in the fluid move along the streamlines in a steady flow. In a small time interval, delta t, the fluid entering the bottom end of the pipe moves a distance delta x, 1, which is equal to the velocity times time. Okay, so that's at this point, the entrance. So if we look at the delta mass, we get rho 1, cross-sectional area 1, and delta x1 equal to rho 1, cross-sectional area 1, velocity 1 with respect to time. The change in the delta m at the exit then becomes the same, but now we have rho 2, A2, V2, delta 2. Because mass is conserved and because the flow is steady, the mass that flows into the bottom of the pipe through A1 in time delta t must equal the mass that flows out through A2, the cross-sectional area, in the same interval. So we have delta, the change in mass 1 is equal to the change in mass 2, which we can expand then to be rho 1 A1 V1 equal to rho 2 A2 V2. So for an equation of continuity, the product of the cross-sectional area of the pipe and the fluid speed at that cross-section is a constant. For the purpose of an incompressible fluid, then rho 1 equals rho 2, which then implies that the cross-sectional area 1 and the velocity 1 must equal the cross-sectional area 2, velocity 2. The condition of the cross-sectional area times the velocity being constant is equivalent to the fact that the volume of fluid that enters one end of the tube on a given time interval equals the volume of fluid leaving the tube in the same interval, assuming that the fluid is incompressible and there are no leaks. Bernoulli's equation. Bernoulli's equation is a consequence of energy conservation as applied now to that same ideal fluid. In deriving Bernoulli's equation, we must assume an ideal fluid then, again, non-viscous, incompressible, steady state flow, and moves without turbulence. So the work done on the lower end of the fluid by the fluid behind it then can be shown as force 1 is equal to the pressure 1 times the cross-sectional area 1. Remember, we define pressure as force over cross-sectional area, so we just move the terms around. The volume then is the cross-sectional area times the distance 1. Okay, so that gives us a value that is cubed. Work 1 then is equal to force 1 delta x1, that's our work equation just like we saw before, force times distance, is equal then to the pressure, the cross-sectional area, times the distance. And then if we take the cross-sectional area and the distance, we get volume. So if we recombine those. Same thing applies with work 2 at the exit. So the volume is the same because by the equation of continuity, the volume of the fluid that passes through the entrance, A1, in the time delta t, equals the volume that passes through the exit, A2, in the same time interval. So the net work done by the forces in the time delta t then can be shown. Okay, so we're going to go back to our fundamental relationships. In this case, the work of the fluid is equal to the pressure times the volume 1 minus the pressure 2 times the volume. Now, if we go back to our definition of kinetic energy, the change in kinetic energy then can be expressed 1/2 mv squared 2 minus 1/2 mv squared 1. And we can bring potential energy into the mix. So delta PE, the change in potential energy, is equal to mgy2 minus mgy1. So the work done by the fluid then can be expressed as the change in the kinetic energy plus the change in the potential energy. So the work in the fluid, if we start with the first relationship up here, P1 volume minus P2 volume equals 1/2 mv2 squared minus 1/2 mv1 squared plus mgy2 plus mgy1. Okay, just pulling in our energy equations and using them where we will. If we go back then to our definition of rho, then density is equal to mass divided by volume. Then we can say, let's divide everything through by volume. So we have, from our expression up here, the pressure 1 volume divided by volume minus the pressure 2 volume divided by volume is equal to 1/2 mass over volume, velocity 2 squared, minus 1/2 mass over volume, velocity 1 squared, plus mgy 2 divided by volume minus mgy1. So since we have volume in a couple of the places here, we can remove the volume, they cancel out. And then since we defined density as mass by volume, let's replace mass by volume with rho for the density. So 1/2 rho v2 squared minus 1/2 rho v1 squared plus rho gy2 minus rho gy1. So all we're doing is manipulating these relationships so that we can come up with something that is meaningful in the world of ideal fluids. So now if we gather all of our terms, all the 1 terms on the left, all the 2 terms on the right, we end up with pressure 1 plus 1/2 rho v1 squared plus rho gy1. The same thing on the other side for the 2 terms. So now we have developed Bernoulli's equation, a consequence of energy conservation applied to an ideal fluid. So there's our relationship, okay, and we can state then that the pressure plus 1/2 rho v squared plus rho gy is a constant. Bernoulli's equation states that the sum of the pressure, P, the kinetic energy per unit volume, 1/2 rho v squared, and the potential energy per unit volume, rho gy, has the same value at all points in the streamline, okay, because we said it was, in fact, constant. So let's look at a little example. A nearsighted sheriff fires at a cattle rustler with his trusty 6-shooter. Unfortunately for the rustler, the bullet misses him, or fortunately for the rustler, the bullet misses him and penetrates a water tank, the town water tank, causing a leak. And we can see up top here, there's where our bullet hole went through. If the top of the tank is open to the atmosphere, determine the speed at which the water leaves the hole when the water level is a half a meter above the hole. So we've got everything laid out in this little diagram here to show where the bullet hole is, where the height is, and the pressure. So if we assume that the cross-sectional area 2 is much greater than the cross-sectional area 1, then the velocity is approximately 0. Okay, so there's our area 2, here's our area 1. Also, the pressure 1 equals the pressure 2 equals the pressure naught. Okay, so they're all constant. So we then pull in the relationship Bernoulli's that we just developed, Bernoulli's equation, and separate our 1 terms and 2 terms on each side of the relationship so that we have the pressure naught the pressure naught added to 1/2 rho v1 squared plus rho gy1 is equal to the pressure plus rho gy squared. Okay, so you can see here on where the bullet hole is, that's our pressure naught. And on the diagram, you can see the pressure 2 is equal to the pressure naught. So gathering our terms so that we can get our velocity on the left side of the relationship, we start moving our terms around so that in essence we end up with velocity 1 squared is equal to 2 times the gravity times the difference in the height, y2 minus y1, and in this case we call h y2 minus y1. Okay, this is the height above the bullet hole. Velocity 1 squared then is equal to 2gh when we make that substitution. v1 then, the velocity 1 then is equal to the square root of 2gh. Insert our values, 2 times the acceleration of gravity, 9.8 meters per second squared, times that 1/2 meter distance, and we get a velocity at the hole of 3.13 meters per second as that water level starts to come down to the height of the hole. Now let's add the problem asks, where does the stream of water hit the ground if the hole is 3 meters above the ground? Okay, so we knew what the height was below the bucket. Now at the edge of the bucket, now we're going to look at the height from the ground to the hole. So we go back to one of our motion equations. In this case, in the y direction, the delta y is equal to v naught in the y direction times t minus 1/2 the acceleration of gravity times time squared. And again, we assume that the initial velocity is 0. So as we start then entering the values in our terms and taking care of our 0 terms, okay, so that first term goes away. We're left with delta y is equal to minus 1/2 g times the gravity of acceleration of gravity times time squared. We have 1/2 9.8 meters per second squared times time squared. So now we know that the height, delta y, is equal to y initial minus y final, and in this case it's 0 minus 3 meters because that's where the height of the bullet hole is in the tank. So minus 3 meters is equal to minus 4.9 meters per second squared time squared when we take half of 9.8. So the square root of t squared is equal to the square root of 3 divided by 4.9 meters per second squared. Our meters cancel out. When we take the square root of seconds, we just get seconds. So time is equal to 0.782 seconds. So that's the time it takes for that stream of water. Now we want to determine, by using the velocity relationship, where the stream of water hits the ground. So the change in x over the change in time, or the time interval, gives us delta x is equal to velocity times the change in time, delta t. So 3.13 meters per second was the velocity that we calculated in the first part of the problem, and then 0.782 seconds is the amount of time that it takes for the water to flow, and it gives us a spot out here on the ground of 2.45 meters is the distance that the stream of water hits the ground if the hole is 3 meters above the ground. So when we come back, we'll look at the last section here, a recap on applications of fluid dynamics.